Hello and welcome to our video on stereo display technologies. In the last couple of videos, we looked at how our eyes perceive the environment, and we found that convergence is the strongest depth cue. So in this video, we're going to look specifically at how to generate images so that our eye's convergence mechanism is activated. For convergence, we need to show each eye a slightly offset image of the same scene, so that we need to show each eye a separate image. A simple way to do this is to have each eye look at a different image by showing a different image to each eye. This is easiest if we can bring the image up close to the eye, although then our eyes can't accommodate to the close distance. The solution to this is to use a magnifying lens between each eye and its image. This is done in the ViewMaster toy that many of you have probably had when you were little, but the same technique is also used in head-mounted displays for virtual reality. Not surprisingly, there actually is a ViewMaster VR viewer. Because the head-mounted approach requires a bulky device with lenses and image generators, other methods to view 3D stereo have been developed. A very simple and versatile one is anaglyph stereo. Many of you have probably seen these pictures that are mostly red and blue or red and green, but when you put glasses with lenses and matching colors on, you can see the image in 3D. If you own a pair of red-blue glasses, try them on this image. Anaglyph's big advantage is that the glasses are cheap and the images can be displayed on any medium, from regular cell phone displays to standard movie screens. There even is a way to see 3D without headgear altogether. Try crossing your eyes to focus on a point in front of the two pictures. You can use a finger to help. Move the finger slowly away from the pictures toward your nose. And focus your eyes on your finger while you do that. At some point, the pictures of the vase should fuse and you should see a 3D image. The concept here is that you're converging your eyes on a point that's in front of the image plane, thus shifting the background images horizontally. This can also work if you focus on a point behind the images. Except then you need to switch the left for the right eye image to see a correct 3D image. A more sophisticated way of seeing stereo images without headgear are stereograms. The approach to view them is the same as for side-by-side images, except that the two images have been combined into one. Try relaxing your eyes to wander into the distance until you see the dolphin in this image. It should look like the black and white image at the top right and come out at you. To make it easier on the viewer, because crossing one's eyes is hard, and it puts strain on your eyes, so that we wouldn't want to do this for the duration of a movie, movie theaters use 3D glasses to show 3D films. With active stereo technology, shutter glasses are used, which shut off one of the lenses and switch between them at a fast pace, usually at least 100 Hz, to avoid flicker. The downside of this technology is that the glasses have to be battery powered so that the built-in liquid crystal can be turned on and off in synchronization with the projector, which needs to be able to run at the same fast refresh rate. Active stereo can work quite well on home TVs and monitors, which is why many 3D TVs use this technology. Because the battery issue is impractical for movie theaters, most 3D movie theaters use a technique that is called passive stereo. Polarization filters in the 3D glasses separate out light that's polarized in one direction from the other. The polarization can be linear, like in IMAX 3D movies, or circular, like in those that use RealD technology. To make this work, the film has to be projected with polarized light, which can be done with polarization filters in front of the lenses of two projectors. Or it can be done with special active filters, which can switch the polarization at a fast rate so that a single projector can show the movie. A downside of passive stereo is that the projection screen has to be polarization preserving. Most traditional 2D movie screens are not polarization preserving, and it can be expensive to replace the screens in a movie theater to support passive stereo, which is why some theaters do use the active stereo approach. It can be more cost-effective to deal with batteries than to replace the screen. Passive stereo can even work on 3D TVs at home. Passive stereo TVs have a polarization filter overlay on them, which polarizes each row of pixels in alternating polarization. The pictures at the top right show how this works. The one on the left shows what you would see through one of your lenses, which is only every other row of pixels. The picture on the right of it shows what the screen looks like when it's viewed without glasses, when you can see all the pixels. The larger picture at the bottom left shows a passive stereo TV viewed through the glasses, where one set of pixels is seen through the left lens, and the ones in between are seen through the right lens. In between the lenses, all pixels can be seen because no filter is in front of them. Both passive and active stereo suffer from what is called ghosting. This is because the liquid crystals used in active stereo and the polarization filters used in passive stereo don't block out light from the unwanted image completely. To remedy this, the company Infotech has patented an approach which separates the spectrum of light between the two eyes. This means that each of the primary colors of red, green, and blue, half of their spectrum is sent to one eye, the other half goes to the other eye. This is done with special color spectrum filters, which are needed on the projectors as well as in the glasses. This technology has the benefit of little ghosting, but there's a slight color shift that comes with it sometimes, and can cause the image to have a slightly different tint for one eye than for the other. A big issue with glasses-based 3D is the mere fact that the user has to wear glasses. And these aren't your regular glasses that you can wear all day long. 3D glasses darken the environment just like sunglasses, and they can make reflective objects look unnatural. How nice would it be if we could view 3D movies and computer graphics without glasses? And it turns out we can, if we use autostereoscopic displays. These displays have a special layer over a regular LCD display to direct the light from the pixels to only one of the user's eyes. This technology is used in the Nintendo 3DS, which has two screens, one of which is an autostereoscopic screen which can show 3D images. There are two types of autostereo displays. One type uses a barrier mask on top of the LCD display. The barrier mask is simply a pattern of parallel lines printed on a transparent background. Knowing where exactly the pixels are and where the barrier mask is, one can calculate from which viewpoints which pixels can be seen through the gaps between the lines. With careful calculation, only pixels that are part of the left eye view are sent to the user's left eye, and only pixels that are part of the right eye view are sent to the user's right eye. The other type of autostereo display uses a lenticular lens mask. Semi-cylindric lenses are etched onto a piece of glass or plexiglass, which is then put in front of a regular LCD display. Again, the light paths can be calculated so that the computer knows which pixels can be seen by which eye. This technique can produce brighter images because no light is blocked, but the lens mask cannot be disabled. Barrier masks can be made out of a separate LCD display, which can be turned off when the display is used as a regular 2D display. This concludes week 1 of our virtual reality course. Next week, we're going to take a close look at tracking techniques.